Let's look at how we can apply this to biological acylation reactions. So if we take glutamate, which is the carboxylate of glutamic acid. So if you look here, here's your amino acid, and here's our side chain, and this is deprotonated as well as this one. So we're in at least slightly basic solutions so that both of these are deprotonated, and the overall charge on this is a -1. So it's glutamate compared to glutamic acid. And now the body wants to form glutamine, and so what we're doing is we're taking this carboxylate here and turning it into an amide. So if you remember from the standard organic reactions instead of biological ones, you can't directly bring an amine in here and replace this because this is already negatively charged. And even if this is an acid and we bring the amine in, then we get an acid-base reaction. So what we have to do, just like we did with DCC and DMAP, dicyclohexylcarbodiamide, we have to activate this to make it a good leaving group so that we can replace it with an amine. So the question then is, how does the body do that? And the way it does it is with phosphates. So it will react with ATP. Now you can look at just the way you did before in any organic reaction, who has electrons, who wants them. So clearly this has a negative charge here, and that's going to be who has electrons. So who wants them is going to be one of the phosphorus with oxygens all over it. And so it will come into this terminal phosphorus, then breaking this bond to the rest of the phosphate group of the ATP. When that's broken, the byproduct over here will be ADP, adenosine diphosphate, as there are 2 phosphates left when it was triphosphate before. And then we'll have this phosphorylated version of our glutamate where we made the new bond between oxygen and phosphorus. And so now we have this phosphate ester plus ADP. So now once this is activated, now we can treat it with the amine. And so again, we can say who has electrons and who wants them. So the amine has electrons. This glutamate ester, phosphoester, can be either one. It's got electrons certainly on these O- and the CO2-, but if you're going to react with an amine, you have to look on here and see what on here will react with the amine. So we can say, okay, so the amine is going to come in to the carbonyl, pushing this electron pair out. And then the electron pair can come back to reform the pi bond, pushing off our now activated leaving group with this phosphate on it. So this phosphate now is a good leaving group, where O-, of course, is a terrible leaving group. And then the last piece of the mechanism, some base that's in solution will come by and remove the proton to get rid of the positive charge on nitrogen to form the product, which is glutamine. So it looks complicated, and it's a biological process with phosphate groups in it that activate. But really, the organic reaction mechanism is nearly the same as most other reaction mechanisms that we would do with carbonyl compounds, where we'd do an acyl substitution reaction, where we first activate. So we have to, 1, activate our leaving group, and then react with nucleophile, just like in other organic reactions.